Welcome. In this lecture, we continue with our discussion on the system level performance analysis of embedded systems. In the last lecture, we discussed techniques for estimating the worst case execution time of a single task. Now, after knowing the worst case execution time of a single task, we must embark on seeing the other issues which influence the end-to-end performance of an embedded system. So, these will be extra task issues which are external to a single task. One such important issue is the contention among tasks which are allocated on the same processor. Now, we saw in the last lecture that such a contention is resolved through techniques known as uniprocessor scheduling techniques. In this lecture, we will go through an overview of two important uniprocessor scheduling techniques, the rate monotonic algorithm and the earliest deadline first algorithm. However, before going into the discussion of these algorithms, we will first recap a few definitions. So, the definition of a task. A task is a sequential piece of code. It can be any sequential piece of code, a C code. We saw in the introductory lecture that these tasks could be control tasks which are executed repeatedly to produce actuation outputs in the embedded system. And each such repeated execution of that task is called a job. So, job is an instance of the execution of the task. So, one time the code is executed, it is said that the job of the task is executed once. Jobs require resources to execute. For example, jobs will require CPU, the CPU or the processor to execute the instructions in the job. It may require the network to pass messages to other components in the system. It may require disks, critical sections, etc. So, jobs requires resources to execute and they have a distinct release time. The release time of a job is the time at which the job becomes ready to execute. So, in the case of a periodic task that we saw in the introductory lecture, we saw that the job is released every time period t. Okay. So, that time period, so if it starts at 0, then 0 is the release time of the job, 0 plus t is the release time of the second job, 0 plus 2t is the release time of the third job in the case of that periodic task. Absolute deadline of a job. The time instant by which the job must complete execution is called the absolute deadline of the job. And the relative deadline of the job, which is the deadline minus its release time. It is the absolute deadline minus its release time, that is called the relative deadline of the job. Now, here we take an example of a single job. So, here is a single job. The release time of this job is 3. The deadline of this absolute deadline of this job is 10. The relative deadline of this job is 7, which is 10 minus 3. The response time of the job is 6, which is 9 minus 3. So, response time is the time at which the output of the job is produced or the job completes subsequent to its release. Now, with these definitions, we now come to a few more characteristics of a task. An important characteristic of a task depends on the nature of the inter-arrival time of its jobs. So, depending on the nature of the inter-arrival times of jobs of a task can be aperiodic, sporadic or periodic. A task is considered to be aperiodic if we have no idea about the inter-arrival times of consecutive jobs. So, the next job can arrive immediately after the completion of the current job, or it can arrive any time afterwards. We have no idea. Then we call this task to be an aperiodic task. So, we do not have any idea about the inter-arrival time of its jobs. Aperiodic tasks are typically event driven tasks, meaning that these tasks are triggered after a certain event certain event occurs. For example, one such task could be the controller for lifting the seat of a car, say. So, when the driver of the car presses a button in order to in order to initiate lifting of the seat, this task is triggered, and before and after that this task is not triggered. So this task is event driven, and hence these are aperiodic tasks which are typically event driven. Tasks can be sporadic. In sporadic tasks, we at least have an idea about the minimum inter-arrival time between jobs. So, when the jobs are separated by a minimum inter-arrival time, they are called sporadic, but we do not have any idea about the maximum inter-arrival time. So, we know that the next job will not arrive before a minimum time is elapsed after the completion of the current job, but it can arrive any time after this minimum inter-arrival time is passed. The other type of task is periodic. Periodic tasks are the most predominant among control tasks. They typically occur as an infinite sequence of jobs, and such sequence of jobs such sequence of jobs arrive periodically at fixed inter-arrival times. So, as we told that, let us say this inter-arrival time is p here and is called the period of the job. So, what we said to be t in the introductory class, we just rename it as p and nothing more. This t and p is same. So, if the first job arrives at time 0, the next job is going to arrive at time 0 plus p, the third job is going to arrive at time 0 plus 2p, and likewise afterwards. So, jobs repeat regularly. The period p is the inter-arrival time, and the inter-arrival time is a value which is greater than 0. The execution time E is the maximum execution time, that is the WCET, which we discussed in the last class. So, this E and WCET is same here, and it is something which is between this E and P. So, it is greater than 0 and it is less than P. So, if the execution time of a task on a certain processor is exactly equal to P, that means that the whole capacity of this processor must be dedicated for the execution of this task, because the execution time is equal to P and jobs repeat every P. So, the entire capacity of the processor has to be devoted for the execution of this task. And with this idea, we come to the utilization of a task. The utilization of a task U is defined as E by P, which is the part of the capacity of a processor which must be dedicated for the execution of this task. So, let us say if your E by P is half, that means that half of the time on the processor must be dedicated for the execution of this task. And we can also say that through this without a lot of deep analysis, we can easily understand that if we have two such tasks of size half, we cannot have any more tasks on this processor, because half of the time will be used by one task, and the other half, which also has an utilization of half, will be taken by the other task. So, no more task can be scheduled on that processor. Okay. So, in this case we have a periodic task here. The periodic task has a p value of 5, p equals to 5, because jobs arrive every 5 time units. The execution of this task E we see is equal to 1. We see that the time required is 1. So, the utilization of this task is U equals to 1 by 5. Okay. So, jobs arrive every 5 time units, and within this 0 to 5 we must execute this job, within 5 to 10 we must execute the second job, between 10 to 15 we must execute the third job, likewise. So, with this idea we come to we will start our discussion on uniprocessor scheduling. So, as we said, uniprocessor scheduling attempts to solve the problem of resource contention or processor contention here among programs running on the same processing element. Here programs and tasks are same. So, given a processor with known computation capacity and a set of tasks with known worst case execution times and deadlines, derive an execution order of these tasks such that all jobs of all tasks can always meet their deadlines. So, this is the definition of what we want to achieve. We want to have a schedule. Schedule means an order of execution of the tasks on this processor such that all jobs of all the tasks which execute on this processor will always meet their respective deadlines. Obviously, for this we must know the computation capacity of our processor, and we also must know the deadlines of our jobs or the deadline of the task. If we know the relative deadlines of the jobs, and WCET is the worst case execution time, that also must be known. One implicit assumption that we are making here is that the deadline of each job is equal to its period. So, which may not always be the case. When this is the case, that the deadline is equal to the period, the relative deadline is equal to the period of a task, of a job, then we call such tasks as implicit deadline tasks. However, we can also have the case that the deadline D is less than period. So, if the task starts at 0, it is P, the deadline could be somewhere here, and such tasks are called constrained deadline tasks. Constrained deadline tasks. So, here in our analysis today, we will look only at implicit deadline tasks in this overview. So, then what is schedulability analysis? The mechanism of determining whether a set of real time tasks can meet their deadlines. The mechanism of determining whether a set of real time tasks can meet their deadline. So, we have a set of tasks which needs to be scheduled on a processor. Will I be able to schedule all the tasks on this processor such that all jobs of all tasks will always meet their deadlines? This analysis, this mathematical analysis is called schedulability analysis. For example, suppose first task 1 comes, we can always understand that yes, this can be scheduled on that processor, on the processor. Every 5 time units I have just one task, one job which has an execution requirement of 1 is going to come, and I will be able to execute. But let us say when a second task comes, will I be execute both these tasks together? How do I analyze? So, we do it through schedulability analysis. Suppose all 3 tasks come, will I be able to schedule all 3 tasks for a given scheduling algorithm? How do I know? We know it through this process of schedulability analysis. And such analysis varies for different scheduling algorithms. Another important criteria is with the deadlines of tasks. Deadlines of tasks can be hard or soft. So, when we have tasks with hard deadlines, the scheduling algorithms are called hard real time scheduling algorithms. When we have soft deadline tasks, we have soft real time scheduling algorithms. So, what are hard deadline tasks? Tasks are said to have hard deadlines when disastrous or very serious consequences may occur if the deadline is missed. For example, let us say task deadlines within a nuclear reactor. If we miss the deadline by by even a very small amount, the reactions may result in an explosion. So, such tasks are hard deadline tasks. Therefore, validation is extremely essential. We must very nicely do schedulability analysis and guarantee that all tasks will always meet their deadlines, even in the worst case scenario. So, we need deterministic guarantees. If the tasks are not that critical, they may consider to have softer deadlines. So, ideally the deadline should be met for the maximum performance. We are allowed to miss deadlines, however, if we miss deadlines, the performance degrades. For example, an example of a soft real time task could be that, let us say we are opening a web page. If the web page opens very quickly, then we are very happy, but if the web page takes a certain, it delays, if the web page delays in its opening, we slowly get frustrated. So, the performance of the system in producing this web page to us degrades, degrades with the time, as it takes more time to open the page. Okay. So, such tasks where the deadline has the essence of a reward, missing deadlines do not have extremely serious consequences, however, has a sense of lower rewards as the latency beyond deadline becomes higher. We call such tasks as soft deadline tasks. So, we use best effort approaches or statistical guarantees for such systems. Today in our discussion, we will only look at hard deadline tasks and hence hard real time scheduling algorithms. So, real time scheduling, as we said, determines the order of real time task executions, and there can be different types of scheduling algorithms depending on the types of tasks and the environment. For example, if the tasks can be independent, where there is no dependency between them, or tasks could be precedence constrained, where the execution of a task, the start of execution of a task could be, or the completion of the execution of a task could be dependent on the output produced by another task. Hence, there is a precedence constraint, the execution of one task must precede the other against independent tasks. Today, we will consider independent tasks. So, in a subsequent class, we will also look at precedence constraint task sets. The scheduling algorithms could be online or offline, meaning that the entire schedule of the tasks, the execution order of the tasks can be determined offline before putting the system into operation. So, I know what will be, I run the algorithm, I know the exact execution order, I store that execution order in the system and use that execution order, that determined execution order, to run tasks during run of the system. That is an offline scheduling algorithm against online scheduling algorithms, where the order of task executions is actually determined when the system is executing, because enough information may not be available offline in such cases. We will look at a few offline algorithms for precedence constraint tasks. Today, we will look at online scheduling algorithms. The scheduling algorithms can have static priority or dynamic priority, meaning that if the priority of the task does not change at runtime, the priority or the relative importance of a particular task with respect to other tasks, relative importance in terms of getting the processor for execution. So, if the relative importance of a task remains fixed during the execution of during execution at runtime, it is called a static priority scheduling algorithm. So, a scheduling algorithm can be online and still have static priorities. The scheduling algorithm can be online and can have dynamic priorities. So, the execution order of the task is decided online, but the relative importance of the tasks with respect to getting the processor will remain static. Then it is a static priority scheduling algorithm against dynamic priority scheduling algorithm, where the relative importance of the tasks can vary. So, we will look at the RM algorithm, which is a static priority online scheduling algorithm, and we will look at EDF, earliest deadline first, which is a job level dynamic priority scheduling algorithm. So, with this discussion, we now look at our first scheduling algorithm, the rate monotonic algorithm. As we said, it is a static priority algorithm and it is an optimal static priority algorithm, which means that given a set of static priority, given all static priority algorithms, if there is a task set which can be executed feasibly scheduled meeting all deadlines by any static priority scheduling algorithm, RM can also schedule it. Therefore, RM is optimal. Why is RM an optimal scheduling algorithm? Because if there exists any static priority scheduling algorithm that can execute a task set feasibly meeting all deadlines on a uniprocessor system, then rate monotonic, the RM algorithm, can also schedule it. So, it at least schedules all scheduling algorithms that any other scheduling algorithm can execute, hence it is optimal. So, it assigns, how does it execute? It has a very simple static priority assignment strategy. What is the priority? It assigns priority according to period. So, the period of the task is the frequency at which its jobs arrive. Lower the period or higher the frequency the jobs arrive, higher is the priority. So, lower the period value, higher is the priority of the task. Higher the period value or lower the frequency at which jobs of the task arrive, lower is the priority. So, a task with shorter period has higher priority, and it executes a job with the shortest period first. So, at any point in time, whichever it gets, whenever it gets a task, whichever task it finds with the shortest period, it executes that. So, it has a set of tasks ready to execute, among that it will choose that task which has the shortest period at any point in time. This is a scheduling policy. For example, here we have 3 tasks T1, T2, T3, and the period of T1 is 4, its execution time is 1, period of T2 is 5, execution time 2, period of T3 is 7, execution time 2. Okay. So, execution time is this length and period is this length. Okay. Now, how does scheduling proceed? So, first at time 0 we all have these T1, T2, T3, all these 3 tasks ready to execute. Now, among them T1 is the task with the shortest period 4. So, T1 gets chance to execute. Okay. After T1 completes execution, so the first job of T1 completes execution, and I know that the second job is only going to arrive at time 4. Okay. So, at time 1, at this time I only have 2 tasks T2, 2 jobs, one of T2, one of T3, and I know that among T2 and T3 the job of T2 has higher priority because it has a lower period. So, T2 completes its execution, the first job of T2 completes its execution. At this point in time, at time 3, what happens? T1, there is no job of T1, there is no job of T2, and therefore, I can execute T3. But after I execute the first part of T3, so T3 has an execution requirement of 2 time units, out of which the first time unit, for the first time unit it can execute. And then what happens is that the second job of T1 arrives. Now, whenever the second job of T1 arrives, we know that T1 having a lower period has higher priority, and hence it preempts the execution of T3. So, T3 is sent from the processor to the ready queue and T1 is brought onto the processor for execution at this time. So, T1 executes at time between 4 and 5 and it completes its second job at time 5. Now, at time 5 what happens? The second job of T2 arrives. So, now because T2 arrives at 5 and T2 has a shorter period than T3, the execution of the first job, the remaining execution of the first job of T3 has to be further postponed. Hence, what happens? Hence, we see that the first part of this T2 executes, and then what happens at 6? We must give T3 a chance to execute, otherwise its deadline is 7 is going to be violated for T3. However, RM decides the priority only based on period. So, T2 still has higher priority at time 6 and hence T2 completes its execution at time 7 and then at this point in time T3 has no more time to complete the execution of its first job and therefore, we have a deadline miss for T3 at time 7. Okay. So, therefore, the rate monotonic algorithm could not schedule this task set. Now, the natural question therefore is how do we understand whether how will we understand whether this rate monotonic scheduling algorithm will be able to schedule an arbitrary task set or not? This, as we said, is done through a mechanism called schedulability analysis. And the easiest schedulability analysis that we have for RM is the utilization bound. So, it says that a real time system is schedulable under RM on a uniprocessor real time system. Obviously, a uniprocessor real time system is schedulable under the rate monotonic algorithm if the sum of utilizations of its tasks is less than equals to n into 2 to the power 1 by n minus 1, where n is the number of tasks. So, n is the number of tasks in the system and u, as I told you, u is E by, so ui is Ei by Pi. Okay. So, this is a guarantee. It says that if I can guarantee this, then I will always be able to schedule my task set. And this utilization bound and the RM algorithm, as for that matter the EDF algorithm as well, was discussed first in a seminal paper by Liu and Leyland way back in 1973. The paper has the name Scheduling Algorithms for Multiprogramming in a Hard Real Time Environment, and it was published in Journal of ACM in 1973. Okay. So, let us take the example of 3 tasks here. We have 3 tasks where 4 P is equals to 4 execution time 1, period 5 execution time 1 for task T2 and period 10 execution time 1 for task T3. For these 3 tasks, we have summation of utilization is what? 1 by 4 plus 1 by 5 plus 1 by 10, which is equals to 0.55. Now, if we calculate this n into 2 to the power 1 by n minus 1, when we have 3 tasks, this becomes 3 into 2 to the power 1 by 3 minus 1, and which is equals to 0.78. Okay. So, this ensures that these 3 tasks are schedulable under RM. Why? Because 0.55 is less than 0.78. So, because this condition is satisfied, I know that these 3 tasks will always be schedulable under RM and will never miss a deadline. But we saw that the earlier task that we saw here missed a deadline. If we go into that, we will see that for those 3 tasks, for those 3 tasks. So, the 3 tasks that we had here is 1 by 4, 2 by 5 and 2 by 7. If we do this calculation, we will see that 1 by 4 plus 2 by 5 plus 2 by 7 is not greater less than equals to 0.78. We will see this. If you just calculate it, you will find this. So, we see that this happens in the worst case. This is a sufficiency bound, not a necessary condition for RM to schedule, meaning that there could be task sets whose utilization is greater than 0.78 for 3 tasks, but they are still schedulable. However, if we have, they are still schedulable. However, if it is less than 0.78, it will always be schedulable. We do not need any other analysis. If it is greater than 0. If the utilization of the task set is greater than 0.78, we need other mechanisms for analyzing. So, more complex mechanisms for analyzing whether that task set will be schedulable under RM. This always considering for 3 tasks in general which we have. If this condition is not satisfied, that is summation ui is greater than this value, then it is not necessary that this task set will not be schedulable. This task set can still be schedulable, but we need further tests to understand whether it will be actually schedulable or not under RM. However, if we have this bound, if this bound is satisfied, we have a very simple test and we can be ensured that the task set will be schedulable. Now, when we have one task, this bound is 1. So, this value is 1. When we have 2 tasks, this value is around 0.8283. We saw for 3 tasks this value is around 0.78, and likewise for n tasks when n tends to infinity, this it goes to around 0.69. Okay. So, we can say that for any arbitrary task set of any big size will be schedulable under RM. So, any arbitrary task set, meaning the task set can contain any arbitrary number of tasks, but for that task set we can ensure that the task set will be schedulable under RM on a uniprocessor system if the total execution, if the total utilization of that task set is less than about 0.69. Okay. But if that is not so, we have to look at other mechanisms of schedulability analysis, and one such schedulability analysis depends on the response time of the jobs of the tasks. We now discuss this analysis method.